All right, still section 2.3. This is mathematical induction. Okay, and it kind of falls into all this recurrence relation stuff, partly because you might make proofs on recurrence relations using this technique, and also, it is kind of the sequence of things, and so it makes sense to put it in here. Okay, so the basic idea is that I want to prove something about a general formula that can lend itself to a recursive kind of situation. Then what I do is I have a statement based on stage n or something like that. Okay, so I have a mathematical statement, a math statement that, kind of based on n, and typically where I could think of n going from 1 to infinity. Now, again, it does not have to start at 1. It could start at -32. It could start at 0. It could start at 5. You just need to know where you're starting it. And we typically would, sort of very generically, we call it, say, Pn. So it's a proposition, P, based on n, or a function of n. Okay, proposition or a statement based on n. Okay, it makes sense now with our subscript notation. Now, what we do in mathematical induction is it involves 2 steps every time. Step 1 is we show P sub 1 is true. And sometimes that's very trivial. But we show that the base for n equal 1 is true. Now, again, don't take that too literally. It's just the first n that you care about. So it could be n equals 0, could be n equal 1, it could be n equal 101. Okay, but it's the first one you care about. And you show that that is true. And again, often that's very simple. And then 2, what you do is, this is the recursive part, is you show that P sub n true implies P sub n plus 1 is true for n greater than or equal to 1. And now you see that recurrence idea at work. Is if I know P1 is true, then if I have this second thing, then that implies P2 is true. But if P2 is true, that implies P3, or any, the case for n equals 3 is true. And so on. And you see, so that gives me a chain that says, oh, it is true for all n. Okay, and so let's look at their example. And they do it with a matrix here. And they say A is equal to 7, 4, minus 9, and minus 5. And they say, hey, show or prove that a to the n is 1 plus 6n minus 9n and 4n and 1 minus 6n. Very interesting. And that's, and that's for n greater than or equal to 1. Okay. Well, step 1, n equals 1. Well, that would mean we need a to be equal to 1 plus 6 times 1, minus 9 times 1, 4 times 1, and 1 minus 6 times 1. But that would mean we need a to be equal to 7, 4, negative 9, and negative 5. But it is. Okay, so great. The case n equals 1 is true. Now, we assume a to the n is equal to 1 plus 6n. Or do they use an n? Or yeah, they use an n. Okay, I'll try to do it like them. Often I'll use a k in this case. I'll say assume a to the k and do the formula. But it looks like what we're doing is simply rehashing what the theorem is. Yes, actually, you kind of are. We're just setting it in there. And so then I have my 4n, my minus 9n, and my 1 minus 6n. Okay, so we assume that. Now, let's look at a to the n plus 1. Well, by definition, our recurrence definition, that's a times a to the n. And this is what we call the recursion step. Okay, we take that next one and we try to write it in terms of stuff that we already know. Okay, and well, we do know a, and the a sub n we're assuming to be true. We're saying, well, if that's true, so this is 7, 4, minus 9, and minus 5 times 1 plus 6n, 4n, minus 9n, and 1 minus 6n. And what we're hoping to get to is, remember a to the n plus 1, well, I should just put, instead of an n in all these spots, I should be able to write it as n plus 1. So let's see if we can do that. So this is equal to, well, 7, 4, the first row, 7, 4, dotted with the 1 plus 6n and the minus 9n. So my first component here is 7 times 1 plus 6n, and then a minus 4 times 9n. So that's the first component, top left. Then do the 7, 4, and the 4n and the 1 minus 6n. So I've got 7 times 4n and plus 4 times 1 minus 6n. And then the bottom row, I get negative 9 times 1 plus 6n. Didn't write that very well. And then minus minus and a minus. I got a minus 5 and a minus 9, so plus 5 times 9n. And then minus 9 times 4n. And the minus 5, so minus 5 times 1 minus 6n. Okay, so that's my result. Can I make it look like the pattern where instead of 6 times n, I get 6 times n plus 1? Okay, well, I'll give it a shot. I've got up here 7 plus 42n minus 36n. Okay. Then over here I have 28n plus 4 minus 24n. Down in the bottom I've got a minus 9 minus 54n plus 59n. And then I've got a minus 36n, a minus 5, and a plus 30n. Whew. Okay, so this is 7 plus 6n, and 4 plus 4n, and minus 9 plus 5n, and what? Minus 5 minus 6n. Okay, well, so 7 I could write as 1 plus 6 plus 6n. 4, I can just tell you that's 4 times n plus 1. 1 plus n, and I just switched the n and the 1. Here, let's see. So what are we heading for? We're heading for a minus 9 times n. Is that what we want? Minus 9 times n. Huh? Okay. So now, let's make sure I did that right. I got a minus 9 and a 54 and a 5n. Okay. So I need a minus 9 times n plus 1. Well, I'm not sure exactly how that would work as I'm looking at it. That's okay. So I know what I want. I want a minus 9 times n plus 1. So I'm going to put it there, and I'm going to add it back in. So 9 times n plus 1. See if I get anywhere here. And then that's minus 9 plus 5n. So I'm a little worried that I might have written something wrong up there, because that just doesn't, right off, it doesn't look to me like that's going to work so well. But hey, I need that, and so I put it in, but took it back out and then left what I had there. And then here, I could make that, instead of a minus 5, I could make that a minus 6. But by doing that, I subtracted 1, so I'll do 1 and a minus 6. That makes minus 5 and a minus 6n. Okay, so up here in the top corner, I have 1 plus 6 times n plus 1. I have 4 times n plus 1, so that's good. Down in the bottom, I'll take the 6 out, and I'll have a minus 6 out. And so I'll have a minus 1 times 6 times n plus 1. And here, I've got my minus 9 times n plus 1, which I think is what I want. And then I've got 9n and plus 9, and then I've got a minus 9, so the 9's go away, but I've got a 9n and a 5n, so it looks to me like I've got an extra 14n down here. I'm not sure what just happened, right? So these three look good, though. Let's look at how they look good, and then I'll go back and try to figure out what went wrong. Okay, so as we look at our formula, right, we're stating that prove that this is true. Well, if I do an n plus 1 here, I should end up with a 1 plus 6, but then times n plus 1, a 4 times n plus 1, and a 1 minus 6 times the quantity n plus 1, right? So if that's an n plus 1, that's an n plus 1, but in parentheses. That's an n plus 1, but in parentheses. N plus 1, but in parentheses. And an n plus 1, but in parentheses. And those three I have, right? If I come back down here, that's what I have. Now, that I definitely don't have the right thing. So probably I made some sort of arithmetic or algebra mistake. So I backtrack. You know, it's not the end of the world by any means. And now let's make sure, I'm going to look back at the example, make sure that I have that right. Yes, it is minus 9n. Okay, so I assume that. Now let's check my matrix multiplication for that bottom one. To get that one, I need minus 9 times 1 plus 6n. Whoops. And, oh, there we go. And then minus 5 times minus 9, which is positive 5 times positive 9n. So there we go. I read that and I said 59. You were probably yelling at me and said, no, it's 45. That makes a heck of a big difference, right? If that's 45, I get minus 9 and minus 9n. Yay! Now, I'll just erase this whole thing. And so then when I can write that as a minus 9n and a n plus 1, which is what we wanted, so that was good. And again, I'll get the right thing here. Minus 9 times n plus 1. And there we have it. We have that if it was indeed true that a to the n was this, then it turns out it is true that a to the n plus 1 is that, which is what we wanted to show. And so it's kind of it's a weird technique when you first get to know it. But it's just kind of this algebraic thing of you just keep trying, you just go back to the base cases and so forth. So let's look at a non-matrix one. I've always liked the formula that if I want to add the numbers 1 plus 2 plus 3 plus up to n, that's just n times n plus 1 over 2. Okay, so to show this by mathematical induction, my step 1 is we'll let n equal 1, and we'll show that indeed if I add 1 to itself, this formula works. Okay, so we have if n is 1, I get 1 times 1 plus 1 over 2, which is 1 times 2 over 2, which is 1. Yay! Check. Okay, it works. It's true for n equal 1. Now we go to step 2, the induction step, and we say, well, assume if we sum up I equals 1 to n, that we do indeed get n times n plus 1 over 2. Now, what we're going for when we, so we want to show, and sometimes it's not a bad idea to maybe write this down so you know what you're trying to head for. If I want to do that, what I need to do is I need to get an answer that looks like n plus 1, right? Because that n became an n, an n there. And then that n here is an n plus 1 plus 1, okay, because it's the n plus first number and then plus 1, and then all over 2. So this is n plus 1 times n plus 2 over 2. That's what I'm trying to show. And so what we're going to do is we're going to take those numbers, 1 plus 2 plus 3 plus n plus n+1. Okay, so there I've added those numbers. Now, the induction part. I'm going to assume I know that that adds to the correct thing. And so that correct thing, remember, is n times n+1 over 2. So there is where I'm using my induction assumption. But now I need to add that n+1. Okay, well, now it's a little algebra and so forth. I need a common denominator, so this is n times n+1 over 2 plus 2 times n+1 over 2. Now I can add those together over the 2. And notice there's an n+1, there's an n+1. Factor it out. And I get n+1 times, and here I had an n over 2, and here I had a 2 over 2. Put those together, and I have an n+1 times n+2 all over 2. And there we go. That was the form I needed to get. And so there my induction worked. I assumed, right? So here's where I assumed that it worked for numbers 1 to n. And so by making that assumption, I could just put the formula in there. But see, I still have that term left over. But then I have to show that these two things do go together to make the correct form, and they do. And so there is my mathematical induction. Okay. So that'll get you started on mathematical induction. It's, like I say, it can be a tough technique to kind of get used to, but once you get used to it, most things are pretty straightforward. There can be some very intriguing, very interesting mathematical induction proofs, but usually these involving, these kind of combinatorial formulas or something like that, where you're just adding stuff up. They tend to really just be, you have to do a bunch of algebra to show it works. And so there we go.